the Spectrum Productions. We are a filming company with photographers, video editors, and scriptwriters with the current knowledge of the latest photography trends and technology.
We encourage students and aspiring photographers to share their passions. Images are more than just a simple record. Photography speaks to the best and most generous part of our human nature, the desire to share what we find beautiful and interesting with others.
That's why today we are going to teach you about how the lenses work, and we all know that lenses are a huge part in photography, right? So let's get started. Of the Spectrum Productions, excellence in every take.
Lenses and refraction. First, let us define what are lenses. A lens is a transparent piece of glass or plastic with at least one curved side. It gets its name from the Latin word for lentil. It means a type of pulse used in cooking. How do lenses work? A lens works by refraction. It bends light rays as they pass through it so they change direction. That means the rays seem to come from a point that's closer or further away from they actually originate. And that's what makes objects seen through a lens seem either bigger or smaller than they really are. The speed of light is affected by the density of the material in which it is traveling. When a light enters a denser medium, it slows down. On the other hand, when it enters a less dense medium, its speed decreases. Types of lenses. There are two main types of lenses known as convex or converging and concave or diverging. Convex lenses. In a convex lens, sometimes called a positive lens, the glass or plastic surfaces bulge outwards in the center, giving a classic lentil-like shape. A convex lens is also called a converging lens because it makes a parallel light rays passing through. It bends inward and meets or converge at a spot just beyond the lens known as the focal point. Second, concave lenses. A concave lens is exactly the opposite, with the outer surfaces curving inward, so it makes parallel light rays curve outward or diverge. That's why concave lenses are sometimes called diverging lenses. And lastly, ray diagram for a lens. The image formed by a single lens can be located and sized with three principal rays. First, a ray from the top of the object proceeding parallel to the center perpendicular to the lens. Beyond the lens, it will pass through the principal focal point. For a negative lens, it will proceed from the lens as if emanated from the focal point on the near side of the lens. Second, a ray through the center of the lens which will be undifracted. Third, lastly, a ray through the principal focal point on the near side of the lens. It will proceed parallel to the center line upon the exit from the lens.
We will discuss light ray rules for spherical lenses and how to apply them in ray diagrams. The convex lens is a converging lens that brings light together to form real and virtual image, depending on the position of the object. Imagine drawing a line representing the principal axis. Mark the optical center O at the center of the line where convex lens will be placed. Mark 2 points to the right of O and label it as F and 2F. Double the distance of F. Do the same thing with the left side. The two F's are the two focal points. There are three rules in image formation through convex lens. Rule 1. A refracted ray of light parallel to the principal axis passes through the focus on the other side of the lens. Rule 2. Rays that passes through the focus after being refracted and becomes parallel to the principal axis. And rule number 3. Rays that passes through optical center of lens go straight. It emerges without any deviation. Notice that rule 2 is exactly the opposite of rule 1, called the reversibility of light. Here are the different images formed by convex lens. Case 1. If object is beyond point 2F, the intersection of two light rays, rule 1 and rule 2, will form an image between points F and 2F. The nature of the image is real, inverted, and smaller in size. Case 2. If object is at 2F, the image will be formed at 2F using rule 1 and rule 3. The nature of the image is real, inverted, and same size. Case 3. If object is between f and 2f, the nature of image will be real, inverted, and magnified. The image will be formed beyond 2f using Rule 1 and Rule 3. Case 4. If object is at f, the refracted rays are parallel and never meets. This image will be far away at infinity. The image will be virtual, upright, and highly magnified. Case 5. If object is between f and o, the refracted rays will be divergent. We need to reduce it backwards to get our image. The image is virtual and erect, magnified, and formed behind the object. Magnifying glass is an example of this. Case 6. If object is at infinity, the rays are parallel and the image is formed at the focus. It is real, inverted, and diminished.
Refraction of light in concave lenses. Concave lenses are also known as diverging lenses that always produce image that is virtual, upright, and diminished or smaller in size. Draw a line representing the principal axis, mark the optical center O at the center of the line where concave lens will be placed. Mark 2 points to the right and label it as F1 and 2F1 and F2 and 2F2 at the left side. There are 3 rules in image formation through concave lenses. The first rule is a ray passing parallel through the principal axis and being refracted away from the principal axis. The second rule is a ray directed at the principal focus behind the lens and being refracted by the lens so that it runs parallel to the principal focus after leaving the lens. And the third rule is a ray passing in a straight line through the center of lens without being refracted. Since the image is virtual, the rays leaving the lens must be traced down backwards in straight lines until they reach a point at which they will cross. This is where the virtual image appears to come from.
And now let's move on to the important applications of spherical lens. First is the uses of convex lens. The first example of convex lens is the magnifying glasses. Magnifying glasses is one of the simplest and direct applications of a converging lens. The object appears at a maximum magnification once you bring the magnifying glasses to an optimal distance. The farther the glass, the object becomes distorted, and the closer the glass, the magnification of the object will decrease. Next is the eyeglasses. Opticians use convex lenses to correct farsightedness or the hyperopia. It is an eye condition that makes the lens of the eye focus on the image too far behind the retina. Cameras. Most camera lenses consist of a converging lens, diverging lens followed by a second converging lens. The first lens controls the magnification level, while the diverging lens flips the inverted image once the light passes through the first lens. And then the final lens inverts the image one last time and delivers the image to the rear of the camera. And that concludes the uses of convex lens. Now let's move on to the uses of concave lens. First example is the binoculars and telescopes. Binoculars and telescopes also uses convex lenses. However, convex lenses don't transfer light accurately. That creates distortions and blurs. That's why they install concave lenses in or before the eyepiece to help focus image more clearly. Flashlights. Concave lenses are also used on flashlights to magnify the light produced by the bulb. The light falls on the concave side while the rays diverge on the other side, making the apparent radius of the light source increase, thus provide a wider beam. The last one is peepholes. Door viewer or peephole is a small security device that provides a panoramic view of objects and environments outside. Concave lenses inside the device minimizes the proportions of specific objects and gives a wider overview of the entire area.
Cameras and the human eye has some similarities. They can produce images that are diminished, inverted, and real. Let's see what parts of the camera has their counterparts in the human eye. Both camera and the human eye has lens. The lens of the camera focuses light onto the photosensitive surface at the back of the camera. The lens of the eye focuses light onto the retina. The camera has focusing screw, which allows the user to adjust focus depending on the distance of the object. Meanwhile, there are ciliary muscles in the eye which stretch or slacken the suspensory ligaments to adjust the shape of the lens. The camera has an aperture which adjusts the light entering the camera in different light conditions. On the other hand, the eye has an iris which adjusts the amount of light entering the pupil. In the camera, there is shutter which adjusts time light enters the camera. Although there are no exact counterparts in the eye, there are eyelids that work just as fine like the shutter. The camera has a photosensitive surface that detects and records light which is focused onto it. The eye has a retina which detects light and converts it into electrical impulses and are sent into the brain. That is a brief talk, and I hope that you have learned from it.
So this ends our discussion, and we hope that you, aspiring photographer or videographer, appreciate and understand the application of different lenses.
We hope that you learned something from us and thanks for watching. Again, we are the Off the Spectrum Productions, Excellence in Every Take.